Hello, my name is Thomas Trausch, and I'm going to have a little presentation about the first proposition of Gottfried Wilhelm Leibniz's work on the quadrature of the circle, the parabola and the hyperbola. And the first step, we are going to draw a triangle, and it's having some points A, B, C. And in the next step, we are going to draw some parallels through these points, like these. And in another step, we just extend the line CB up to the point that it's normal, somewhere meets exactly in the point A, like this. And from each point which intersects now this the horizontal ordinates in some place, we're going to now draw verticals like this. And what the theorem says in this proposition is that the original triangle ABC, which we drew out at the first place, is equal to the half of this rectangle MRFN. And in order to show this, it may not be quite clear at the moment why he needed to prove exactly this relationship, but this is going to be shown up in a later proposition where he is defining some relationships between the circle and another figure which is similar to the circle, and which allows him to draw out some proportions. But for now, we're going to just show how to prove that this triangle A, B, and C is equal to the half of this rectangle. And in order to get there, you actually need to work with the similarity of triangles. Yeah. So he said that the upper red triangle is similar to the lower red triangle. And it is also clear from the way we constructed these that these two triangles both have a right angle involved. And it's very generally also clear that each of these triangles has a total sum of their inner angles of 180 degrees. So combining these two information, we can say that we only need to know one more angle of these two triangles to be equal in order to state that these are similar. Alright? And the way we're going to show this is by just moving this upper triangle in a sort of a parallel shift across the line HGBC down to the point such that both triangles are attached to point B. Yeah, like this. And we see now that both triangles are attached in a way now that the former line AG is now attached to line B of the lower triangle, sharing the same line. And the same applies to the former distance HG, which is now attached to BC of the lower triangle, and they're also sharing the same line. So you basically have an intersection of two lines, and according to the Greek scientist Thales, we know that if you have intersecting lines, the angles which are created by it lying opposite to each other are equal. And this way we have now the information that two of these angles within both triangles are actually equal. So this is the same angle as this one, and the right angle, of course, is the same right angle as in the lower triangle. And hence it must be that the third angle is also equal. So in this is telling us that indeed these two triangles are similar. So how does this help us? We're gonna go now to the next steps. which lead us to proof of the theorem. And remember, the theorem was that the original triangle ABC, shown up in green here, is equal to the half of the rectangle MRFN, which is shown in brown here. Yeah, and when you have a similarity, you are basically able to compare proportions of each triangle, or sides of each triangle, to each other. So we have these little equations up here. So it says, for instance, that the proportion between the side AH and AG of the upper triangle is equal to the proportion of the same type of sides of the lower triangle, being CE to CB. And ergo, when you rearrange this equation a little, you can create products. So if this is true, it must also be true that the lines AG multiplied by the line CE of the lower triangle as an area is equal to the area of AH multiplied by the line CB. So in order to make it a little bit clearer, we're gonna formulate now rectangles of these sides involved in the proportions. Okay, we take this two sides from the upper triangle, AH and AG, and we make up a rectangle of those. And the same for the lower triangle, and using the sides CE and CB. And of course, because of the similarity, you will get proportional rectangles, which means they have the same sort of ratio between one side and the other side, and hence they are sharing the same diagonal. So, and considering this information, we can now basically rip the blue rectangle apart and the black rectangle also apart and formulate new rectangles, which may look different, but of which we know, because of the similarity of these triangles, that they must be similar, or they must be equal in area. So let's continue. So we take of the black angle, the black rectangle, we take the side AH, and of the blue triangle the side CB, and we form a rectangle out of this. And when we do the same thing for the side AAG of the first triangle and CE of the lower triangle, then we get this rectangle. And you see that they are looking different in the proportions of their sides, but that they originate from a relationship of similar triangles, we know that their areas are equal. Okay, and now we're going to look in the next step where they fit in our little construction here. And you see that the rectangle AGCE is exactly our rectangle MRFN, and the other rectangle, namely AH and CB, is basically this one being attached to the line CB of the lower triangle. And we need to prove, again, to remind you of the aim of this proposition is we need to prove that this triangle ABC is equal to the half of this triangle, of this rectangle here. So how we're going to do that? When you look at the whole construction, you immediately see that you can make up a lot of different triangles, and you can draw out relationships between them, which we will do now. So you have, for example, the relationship of the large triangle AHC, which is this one. And if you subtract from it AHB, which is this one, no one probably will doubt that the result of this will be our triangle ABC. So in the second step, we're just going to double each of these terms representing triangles. And when you double a right angular triangle, you usually get a rectangle. Okay, let's look at this. So we double each term, which keeps the equation still to be true. And when we look at the rectangles now, as a result of a doubled right angular triangle, you see that 2AHC is this right angle, and when you subtract from it 2AHB, which is this triangle, you get, as a result, 2ABC. Okay, and now you see that this is defining the relationship now, because the triangle, or the result of this subtraction from this one and this one leads to 2ABC, which is exactly the same rectangle which we drew out from the similarity of our triangles here. And we know from this relationship that the rectangle AHCB, this one, is equal to 2ABC, yeah, which is the double of our original triangle ABC. Okay, so, and since we also in an earlier step were showing that these rectangle and this rectangle were equal, so it must also be the case that the half of the rectangle AG times CE, which is this one, is equal to ABC, which is our original triangle. And hence we have proven that our triangle, our original one, ABC, is equal to the half of this rectangle MRFN, or as we call it here, AG and CE. And this actually becomes important, this relationship, just the proportion between these two areas, this one and this one, is basically 1 to 1. Yeah, they are of the same area. Alright, so we proved what we needed to show, and I hope you're gonna join us for the next proposition again, and I hope you enjoyed it a little. Thank you very much. Bye bye.